The topic I'm going to cover today is based on work that I did just slightly before my retirement, 2 or 3 years before my retirement. And it involved a team of scientists from Australia, France, United Kingdom, China, Hong Kong, and the United States. So it's an international project, but it's a small project with just some seed funding. INQUA is a group specializing in the last 2.4, 2.6 million years. They are a multidisciplinary scientific group, and they had a project called Subaerially Exposed Continental Shelves since the Middle Pleistocene Climatic Transition. There's also an IGCP project 526, which is supported by UNESCO. So I was involved in the project, and for some strange reason, I'm supposed to be the leader. Errors made by Al Gore in Inconvenient Truth, there are 2 main ones. Carbon dioxide was driving temperature rise in this ice cores. And the current level, it was slightly less than 400 in those days, but it's at an all-time high, according to Al Gore. If we look at the carbon dioxide in the ice core in Antarctica, based on several ice cores, they have this combined record of 800,000 years. And the general assumption for the warmest is that there will be runaway CO2 warming in the present day, because CO2 is going up at a rate of about 2 to 3 parts per million every year, based on the record in Mauna Loa, the big island of Hawaii. INQUA is a group who believes that interglacial glacial cycles were caused by Milankovitch cycles. And this is clearly real climate change because the temperature difference is sufficiently large. We're talking about at least 10 degrees Celsius. So not just 1 to 2 degrees. But why CO2 lags temperature rise? And the consensus is about 600 years, plus or minus 400 years. So it's quite a large error by bar. What we do not know so much is the vegetation history of subaerially exposed continental shelves and oceanic islands. So these are the coral reefs. Because we haven't drilled into these areas to study them, except for a few locations. The reconstruction of the pre-industrial record is quite clear from these subaerially exposed continental shelves and oceanic islands. We don't have any industry in the early days. The age of the Holocene marine deposits is relatively certain. If we drill a hole into the continental shelf or into an oceanic island, we can clearly distinguish it. If they have never been subaerially exposed, they will contain all the marine shells, and they are preserved very well. Episodes of subaerial exposures of continental shelves and oceanic islands during glacial periods are indicated by soil development when the sea level retreated, often down to an order of about 130 meters. So we really need to study sea level changes using drill cores. And stable continental shelves like in Australia and parts of Eastern Asia, including South China, are quite ideal for this purpose. The Vostok ice core record done by the Russian in the 80s turned out to be about 3.75 kilometers in length. So it's a long tube of ice from the top all the way downward until the bottom. And they found a lake called the Vostok Lake. And based on this record of ice, studies have been made on the ice to get a high resolution record of temperature change, CO2 composition, and so forth. You can actually see the bending on this slide, annual bending. So, and this is the original drill site and the location of it in terms of the topography of Antarctica. So we are talking about these annual layers that has accumulated almost every year. And based on the study of this ice core, we come up with this record. The diagram at the top is carbon dioxide. The middle diagram, the red line, is deuterium, which is the temperature proxy. The best temperature proxy, heavy is deuterium. The carbon dioxide fluctuates between 80 to 100 parts per million difference between glacial and interglacials. So we're not talking about very large changes. Note that the glacial terminations are always very abrupt, while going from interglacials is much less abrupt. So you can see that in the bottom graph in all these diagrams. You can see it. The sharp termination. So the Holocene is on the left-hand side, and then the second peak that you can see is the last interglacial, third last interglacial, fourth last interglacial, fifth, and so on. This is quite a rare map based on a French lady, Nicole Petitmeyer, who tried to reconstruct vegetation history during the last glacial period. I'm afraid the scale is not very good, but you can see the present day is shown in the top map. The bottom map shows the extent of the ice during the last glacial maximum. So this is the maximum extent of the ice coverage 21,000 years ago. And then the vegetation, including the continental shelves. During these low sea level stand, we're talking about a land area increase of roughly about 8%. So there'll be a lot more land, including those covered by ice, by the ice sheets. ClimeMap is an international project trying to map the world at this time period, the last glacial maximum. But there's still a lot of uncertainty. They use temperature proxies, and this is a summary of what they think is happening. The temperature distribution at the time. We are fortunate to have multiple methods of dating of these deposits when we have drill hole samples. First of all, we can use the sequence stratigraphy, the marine layers and then the terrestrial layers. Marine layers are formed by high sea level. Terrestrial deposits are formed by low sea level sands during the glacials. Usually you have alluvial sediments. We have multiple methods of dating. The direct methods are listed here. Radiocarbon, uranium series, luminescence, amino acid racemization, cosmogenic dating. While the indirect methods include fossil content, magnetic susceptibility, density, and moisture content. And we can make use of ice cores, deep sea cores, and lowest deposits. So all this have been worked on by different groups of people in the INCWA, scientific groups. So it's quite well known, except other people are not so familiar with it. An example here is the reconstruction of the sea level rise after the last glacial maximum. One of the problems with this sea level curve is that radiocarbon becomes ineffective when it's over about 10,000 years. We have to rely on other methods of dating, and this is a bit problematic. But basically, using radiocarbon dating, we can identify meltwater pulse A, 1A, based on locations in Tahiti, Barbados, and New Guinea. So, what happened during the last glacial maximum? All these oceanic islands, we can find blue holes. And why do we get blue holes? And this is a residue of karstification when sea level was much lower, subterranean drainage. So on carbonate platforms, like Great Barrier Reef will be a carbonate platform. On parts of the coral reefs, you may have these features developed. This example is from Belize. It's just one of the blue holes, but many locations we do have these blue holes. So divers can go into it and go down to depth of more than 100 meters or so and find subterranean drainage and so on. Questions to be answered in order to explain why CO2 lags temperature rise by as much as 600 years. We will study paleoenvironmental change during glacial periods, sea level change, what role exposed shelves and oceanic islands have in the global carbon cycle. So particularly the vegetation history, including the migration of fauna and flora, land bridges, human migration, vegetation change, and what happened to coral reefs when they were left high and dry. We have different methods useful for dating, and then we can correlate between land and sea, and then hopefully we can link up the solar variability, and of course, which is very difficult for past records, which are old, role of volcanoes in regional warming and cooling. Not like the present day when we have satellites and so on. In our group, I'm mainly responsible for South China Sea because I work on the continental shelf of Hong Kong. So there are different types of continental shelves. South China is a siliciclastic dominated continental shelf. It's a muddy shelf because of the River Pearl. So siliciclastic means it's made of silica and clay, basically, muddy shells. This is a last glacial maximum map of Sundaland, extending from the South China Sea continental shelf all the way to the Australian coastline, northern coast of. The black dots are where we have ocean drilling program, drill holes that has been studied for their ages and fossil contents and so forth, including oxygen isotope, which provides a proxy for temperature change. You can see the isotherms, 18, 20, 22, 24, 26 degrees, and so on. So basically, the Pacific Ocean and the Indian Ocean becomes almost isolated. The through flow ceased during the last glacial maximum. In terms of dating the base of the Holocene deposits, we have the M units, which are the marine units, and then the T units, the terrestrial units, labeled 1, 2, 3, 4, 5, and so on. So we have 5 interglacial glacial cycles And the estimated age is shown in the third column, the marine isotope stage, and then the absolute age, the method used for the dating, and so on. The maximum thickness of the cores we are able to identify is shown in the last column. So in Hong Kong, we rely heavily on these engineering drill holes to study the sedimentary sequence, to study these siliciclastic deposits. So this is a diagram you've seen before. So basically just focus on the middle diagram where you have the deuterium or the temperature curve. So we are able to identify these 5 cycles, M1, M2, M3, M4, M5. These are the high interglacials. And then the low sea level stands are the T1, T2, T3, T4, T5, and so on. And that's the record available from Vostok Ice Core. The record has since been extended by taking another ice core at Dome C in Antarctica. So this is shown in the bottom diagram and then the middle diagram, so on. So you are able to extend it to at least 3 more interglacials. So this is the sedimentary records we can see in the ice cores. But in Hong Kong, we can only see 5 cycles. Radiocarbon dating has also enabled us to identify a global event which is important in many parts of the world, the 8.2 Ka event. This is the meltwater pulse from the melting of the Laurentide ice cap in Canada. So it's marked down here at 8.2 Ka, 8,200 years. So usually the basal deposits on the continental shelf, you tend to get this maximum age. We were fortunate in the 90s to be building this Hong Kong International Airport at Chek Lap Kok. It's quite a major project. The reclamation involves 75% of the world's dredging fleet. And you can see the airport platform after reclamation with this pinkish color sand. The bottom corner shows an example of a borehole. It's a continuously sampled borehole. The top 1 meter you can see is grayish green in color. The M1 deposit is labeled, resting directly on another marine layer, the M2. In fact, there are no T1 in this sequence. So the length of these sections are 1 meter. So we're talking about 3.4 meters of M1 or Holocene marine deposits resting on top of a second marine layer. The upper part of the marine layer is more or less bleach in the color. And then deeper down, you can see mottling, oxidative environment. So the M1 has never been subaerially exposed, and that's why they retain the reducing colors. While the M2 marine unit has been exposed during the last glacial maximum. And you can see iron cementation in part of the M2 unit, and this is explained by iron cementation pathogenesis. Some boreholes that we have studied, I think just pay attention to this diagram on the right-hand side. This is a longer borehole that goes down to 4 marine layers, M1, M2, M3, M4. And what we have done is, in the same borehole, we've taken fixed volume samples of about 2 centimeters diameters, and we have measured the water content. We just weigh the sample before drying and weight it after drying. And this is plotted in this graph, and you can see M1, the grouping of the moisture content, more or less all saturated. So the moisture content basically tells you the stratigraphy of the borehole without using any dating. On the upper part of the M2 unit, the desiccated crust, you see lower values. Then at depth, it increases slightly again. M3 is again the same, but it depends on the permeability of these deposits. So basically, you can see desiccated crust formed during subaerial exposure of these interglacial deposits every time when you have a low sea level stand. The other diagram, I think it basically just shows the iron content that we have measured, which is consistent with pathogenesis. We also have measured particle size, classifying them into clay, silt, sand, and so on. Some photomicrographs of these deposits in the desiccated crust and in the marine deposits. In the M1 unit, you can see microfossils like foraminifera. So all these circular bits, they are all forams. This is a diatom, this elongated one. This is a rootlet growing in the deposit, and the black is pyrite frame voids. It's metallic, so this is why light doesn't pass through it. It's a metallic element. And this is a worm burrow filled in with sand. So in the desiccated crust, often you have, during the early stage of the Holocene transgression, burrow organisms like crabs and so on, digging holes into the pathogenic layer of the desiccated crust. Desiccated just means it's iron cementated. And here is the key. In one of the desiccation cracks, we can find halite crystals, salt crystals. So this gave us, for the first time, some clues that the subaerially exposed continental shelves are highly saline. And this may require time to be removed by leaching, providing that water can infiltrate into these low permeability deposits. But whether it can take up to 600 years to remove all the salt before freshwater vegetation can colonize these areas. In terms of strength of material, this is quite stunning in a way. The Dutch cone test, they push this cone into the seabed and it measures the strength of the soil continuously. And every time you hit this desiccated crust, you have a change in physical properties. So much of the airport is studied using these Dutch cone tests. And the bottom diagram, you can actually see one of these profiles. The desiccated crust at the top, there may be more cracks, so it's lower in strength, but at the bottom, where it's more cemented, it's much stronger, and so on. And another one. So you have two marine layers, M1 on top of last interglacial marine deposit with a desiccated crust here. And this rests on top of alluvial deposits in this particular location. In a longer continuous borehole, we have different types of drilling methods. This is using a case fiber coring method. It's a drill hole continuous down to 25 meters. And we use this magnetic susceptibility device to measure the iron content, basically, of these core sediments. And you can see a shift at the boundary between M1, M2, M3. I think you have terrestrial deposits down here, so they're much more sandy. Somewhere in between here is our boundary, or between the M2 and the M3, up to 3 layers of marine mud. Hong Kong is a busy place, and these are the seismic coverage that we have. So it's one of the most studied place using boomer seismic in the world. The marine seismic can also be interpreted to support our conclusions. So this is actually the sound source towed behind our boat, sea boom. So you can see our classification of our borehole, M1 on top of M2. In this case, you have a little bit of T1, then M3, M4, M5. So Hong Kong have up to 5 marine layers. Very commonly, in some sites, the basal sediments has a lot of plant materials. And this led to the release of methane, which makes the record very confusing, what we call acoustic turbidity. So it's just basically blank, so we can't see the clear-cut boundaries anymore. But these are pockets where you have a lot of organic matter from dead plants. And the bacteria are feeding on it, releasing methane. And this is why the record is like that. It's gas blanking. Examples of shallow seas with carbonate-dominated platforms and oceanic islands, in other words, the atolls, New Caledonia, Great Barrier Reef, Mururoa are examples that has been drilled. I'll go through some of these drilling. In New Caledonia, they can drill on the coral reefs using this type of rig. In Great Barrier Reef, they also have been done. The result. So here you can see one hole from Caledonia and one from the Great Barrier Reef. The ribbon reef is a bit small, but I hope you can see it. At the oldest they can find is marine isotope stage 15. 13, 11 is a much longer record compared to Hong Kong. And marine isotope 9, 7, 5 is the last interglacial. And the Holocene is up here. So it's quite a long record, similar to the ice core that we can find. So these are very important records, except that these are all made of coral reefs. Angle drilling has also been done in Mururoa, in these atolls. And again, based on the study of these corals, they can date and come up with records. So for example here, all the way up to marine isotope at least stage 9. So these are high stand. Every time sea level becomes stable, the coral reef grow a little bit. And this is repeated in the sequence. So what can we say about what happened to these exposed continental shelves and oceanic islands? Some of the chemical reactions in muddy shelves are summarized here. Marine deposits off river mouth tends to have lots of pyrite from plant remains wash into the bottom of the deposit, the base of the Holocene. They tend to accumulate in basal materials. And this led to formation of pyrite frame buoys because of the reducing conditions of the sea floor. The iron is reduced to ferrous. But when you have subaerial exposure, you have oxidation of the ferrous, the pyrite, into limonite. The hydrogen ions and the sulfate ions from the oxidation of the pyrite forms sulfuric acid. And the sulfuric acid is very important in terms of reacting with the calcium carbonate, in terms of shells present. to give gypsum, water, and carbon dioxide release. So this is the source of carbon dioxide released from muddy shells. So the plant matter is responsible for the release of methane. The ferrous ions and the carbonate ions led to formation of minerals such as siderite, iron carbonate, which we have also found in these boreholes. Chemical reactions in carbonate shelves and oceanic islands. So every time when we have a low stand, we have karstification, limestone country development, forming these blue holes and so on. Right? So basically, carbonic acid is formed, and this causes the limestone to dissolve, forming the blue holes. And eventually they are precipitated lower down in the sequence. So gas is again released. So the carbon dioxide story clearly lacks temperature rise as a result, based on the fact that it's consistent with the vegetation history in that the early stages of subaerial exposure, the continental shelves and the oceanic islands were highly saline. And freshwater plants find it very difficult to colonize until all the salt has been removed by flushing, by leaching and so on. So, some conclusions. Antarctica ice core shows a record of gradual change to interglacial periods and abrupt change into glacial periods. The high salinity of subaerial exposed continental shelves and oceanic islands explain why carbon dioxide lacks temperature rise in Antarctica ice cores, because vegetation needs time to adapt. Exposed siliciclastic-dominated shells and carbonate platforms were affected by acid-sulfate soil development and karstification, respectively. But we really need to study more of these locations to confirm the vegetation history. At the moment, the sites are still rather limited. Continental shelves is one area that needs a lot more information in order to support this idea. Thank you very much.